this activity uses the FET animation called the ramp, and you can Google the ramp and FET to find it. I'm just going to run it straight off the internet. Here's the screen that comes up, and the default object here is the file cabinet. I made the rest of this video thinking it was a fridge because I wasn't even looking at it. So when I say the word fridge, I'm really meaning this file cabinet, because what you can see, you can do this with a fridge, which is just a little bit heavier than the file cabinet, which is conveniently been chosen to be 100 kgs. So I did my exercise with the file cabinet. You can actually use any of these objects. In fact, you can even choose the sleepy dog if you want to, and you should get the same effects. But obviously the sleepy dog's only 15 kgs. It's quite a light dog, and it's going to slide up and down just the same. There's no animal cruelty in this, so if I make the slope frictionless for the dog, off it goes, sliding off and crashes into the wall. No animals were harmed in the process of making this video. I hope you find it useful. This is the ramp program. We make the ramp frictionless, and first of all, watch what happens. The fridge obviously accelerates down the slope, and we can put the fridge anywhere we want to on the slope by dragging it, but it's actually easiest if we do it using the position slider. So, oh, it keeps running away. To stop that happening, just press the pause button, and then we can position the fridge in the middle of the slope. And what you can see is that there's a small downwards force down the slope. That's what's accelerating the fridge at the moment, because its weight force has got a component down the slope which is not balanced by the normal force. So I'll clear those graphs to get those out of the way from confusing anything, and point out that here we can introduce a parallel force up the slope. So if we slide this, we can increase the force that the person is applying up the slope, and if I unpaused it now, it would accelerate up the slope, because I've got a total up the slope. Just show you that. So click on pause to unpause it. Oops, sorry. Click on go to unpause it. Not surprising there. Okay, so I'll pause it again. Put the fridge back in the middle somewhere. So I've put it at 7, doesn't really matter. At the moment I've got too much force going up the slope, and this is the tricky bit in this experiment. We need to adjust this until there's 0 total, and it's quite a small picture. So if I've gone too far that way and too far that way, so the technique is to go too far in both directions and try and find something in the middle. So what I've got at the moment is I've got a 10-degree ramp, and I'm finding that the applied force that I need to apply on here, I can read that off here, and it's 178.41 newtons. Okay, so that's my force at the ramp, and that's my angle of the ramp. And the activity is to try and find out how the angle is related to the force. So pretty simple. I'm just going to put in another angle, 20 degrees, and tell it to go, pause it, and of course I need to adjust this force again, and so I need to look for making that total 0. Not it, not it. So I'm trying to get a line in the middle of there. So I'm going to say that 173.45. Which doesn't seem. So I have my 10-degree slope. Now I want to have a 20-degree slope. So put in 20, hit return, and the slope's got a lot steeper. I need to work out what is the force needed to hold that fridge. The moment it would accelerate down, so I need to increase the force slightly. So I'll grab the slider and take a reading, 327.29. 327.29. And what I'm going to do is going to keep repeating this for angles up to 80 degrees. So let's go to do it at 30. If it'll fit. $491.06. That was at 30. See if I can do 40 degrees. I've got a problem here because I can't see it. To take readings at higher angles, we're going to have to make sure the fridge is down at the bottom of the slope or it disappears off the screen. But here I am, I've set the fridge at 40 degrees and I need to adjust my applied parallel force, and I'm looking again for that total to be 0. Here it is. So I'm taking a reading of 620.1. Okay, I'll carry on taking the readings up to 90 and fill the rest of this table in, but what I'm also interested in is to know how accurate these values actually are. I've filled in the table now with the angles up to 80 degrees, and what I can see very obviously is that as the slope has got steeper, the force I've needed to apply to hold it steady has increased quite a lot. I can see also that there's less effect of 10 degrees when I'm going from 70 to 80 than there was when I went from 10 to 20. So I seem to have a curved trend, but what I'm going to do is just to check for the accuracy of this. I don't actually believe I've got 5-figure accuracy down here. So what I need to do is to go back again and just have another go at taking all the data. I could take the angle again when I did 10, but actually coming back to it fresh is more fair. So I need to reduce this down now until I get the total to be 0, and adjusting it one way and the other to find that middle point. This time I've got 168.48, which is way off from what I was before. So write the whole figure down, but bear in mind that really it's about 1.7, and I need to go right up the table. I'll probably need to do it 3 times to get any consistency in my data. If I'm plotting this in Excel, what I can do is I can plot the angle against these values, and what I would do then is I would just make sure I'm filling in a table down here, putting the values in, the repeat values down here, rather than putting them in a table like this, because what that means is I can plot the graph as I go. So highlighting this whole area here, I'll just maximise Excel so we can see what we're doing. Go to insert a scatter graph, put it in here, and there we can see, here's the graph that I'm plotting. I'm plotting the force against the angle. The angle's not going to go over, just leave that for now. So I can have this graph and see how it's looking as I go. And so as I fill this table in, these points will go into the graph now. Just get rid of that and make my graph just nice and handily small. So let's Let's go back to plotting the 20-degree one in. 20 in there, and change my applied force. So 342.18. And what's happening, you can see these points are appearing. They aren't as far off as you would have thought from looking at these numbers. So actually plotting them straight onto the graph is quite nice. As you can see that there's no real point in worrying about the fact that there's a little bit of inaccuracy, because I can see it's not affecting the trend at all. So my next angle is 30 degrees. And adjust this, and I'll just keep doing this and fill up the table with 3 sets of points, and you can try that too. Finally, I finished all my measurements, and so what I can do now is look at the Excel chart and see what's happened. So I've got all my data in these columns here. I'll just make it a little bit bigger so we can. So you can see how the angle has affected the force, and as expected it's increased. There's one point a little bit off there, but in general I can see there's a clear trend. You could just print that out and draw the trend line in yourself. What I'm going to do though is I'll right click on it and I'll ask it to add a trend line. It's clearly not a linear trend line, and I'll just tell it to try putting in a power in here. That doesn't work. Polynomial, maybe. So that's showing roughly the trend on that. It would actually appear that this data point here, this one, which is a 60, which is reading 274.02. I'll hover over it and I can see that. What I've done here is you can see that I've made a mistake. It's clearly a mistake because this is the same as the 50 reading. So I've obviously not taken the reading correctly. So what I should do is just do that 60-degree one again and delete that one. So if I delete that from there and delete it from here, I can put the number in again. So I need to set this back to 60 and just do it one more time. And this time it's reading 853.35. Very different. 853.35. And make sure that all of those data points are showing on here. Don't want to see the line, I want to see the series. Get rid of the trend line a minute. Delete the trend line. So here's the series here, and all of the points are being plotted this time. So clearly that 60-degree one is just fitting in there with all of the others. Right on top of them, in fact. So what's the trend line? You can see that mathematically, for the fridge to be in equilibrium, the force up the slope, F, is got to equal W sine theta. Look at this triangle and you can see this is the equilibrium triangle, that's theta. W is fixed by the weight of the fridge, and that force has got to close the triangle to keep it in equilibrium, so that's got to have the length of W sine theta. Remember, sine theta is opposite over hypotenuse, so this length here is going to be W sine theta. So W is fixed, so we'd expect a sine theta relationship. Let's just have a look then at working out the sine of the angle. Now, sine in Excel is a little bit tricky, and you might just prefer to use your calculator, because your calculator you can have set to working in degrees, and then just work out sine of 30, So press sign, put in 30 equals, and you should find that comes out as 0.5. Now if I use the equations in Excel, if I write equals here, then I can choose a sine function, but if I use that sine function and click on there, what you'll see is it says it returns the sine of an angle, and the number is the angle in radians for which you want the sine. Now radians is another measure of angle which you may not have met yet. It tells us here that degrees is times pi over 180. Which is, what you'll learn is that 2 pi radians, that's the one whole rotation, is the same as 360 degrees. And so what I just need to put brackets there. So I'm putting close brackets and then slash 180 and hit return, and now I've got the angle in degrees. So this is the function I need to be using on all of these angles over here. So here I'm working out equals sine, but I don't want E2, I want, at the moment it's going to be A2. So I want the sine of that there. So sine of A2 converted into radians is this. You might just want to check 1 on your calculator before you carry on. And now I can drag down here and get all of my values in radians. The 30 degree one's coming out as 0.5, so that's fine. So I was looking at how the angle affected the force. I want to have a look at how the sine of the angle is affecting the force now. So I'll just do the easy way to do this. So this is sine angle on the top of this. And if I just copy this whole bit of table here, I can then plot this graph. So here's my angle against my force. Insert the scatter graph here, and it does look like I might have a linear relationship. Oops. What happens if I add a trend line? It does seem to be a pretty good straight line. I can display the equation on the chart there. It isn't quite going through the origin, but I don't think it'll make much difference if I make it go through the origin. That 4 isn't very big. So if I format the trend line again and tell it to set the intercept at 0, 0, then that will get rid of that. And you can see that I've got here the y equals 780.9 times x. So my x was sine theta. I'll just put in theta as a th at the moment. And my y was the applied force up the slope. Label the axes. The vertical axis is applied force, and it's in newtons. And then the axis title underneath here is the sine of the slope angle. This can't go more than 1, so I'm going to get rid of that by formatting my axis and telling it I've got a fixed maximum of 1. I'll get rid of these because they're not being helpful at all. And there we've got good answer, which is giving us a f is 90 sine theta. What did we think we were going to get from the book? Well, we thought that f would be w sine theta. So what we can do now in our physics thinking is we can think, well, what was the weight? Because I'm thinking the weight of this fridge is probably about 780 newtons. Let's go back and have a look at the ramp itself. And here we've got the fridge was 125 kilograms. Oh, sorry, no, we're working with a filing cabinet. The filing cabinet is 100 kilograms, so we would expect it to have a weight of 100 times 9.8, so that'll be 980 newtons. And look, 980 is the slope of our graph. And yeah, physics works.